Hello everyone, I am Muskan from BSc Chemistry Honors first year. My roll number is 21. Today I am giving my presentation for physical chemistry. So the first question is, what is second law of thermodynamics? The second law of thermodynamics states that while energy can be converted from one form to another, the total energy of an isolated system remains constant. However, a significant portion of the energy is lost as heat, making it unusable for work. This means that for every energy conversion, some energy is inevitably lost and the universe entropy increases. Heat always flow from a hotter body to a colder body spontaneously. The natural processes are not reversible without external energy input. Entropy increase. The entropy of the universe always increases during spontaneous processes. It is impossible to convert all heat into work with 100% efficiency. Example, if a hot thing is put in contact with a cold thing, they both achieve the same equilibrium temperature. After separating the item, the equilibrium temperature remains and does not naturally return to its initial temperature. Third law of thermodynamics. Third law of thermodynamics states that the entropy of a pure substance in a perfect crystalline state at zero temperature is zero. The third law of thermodynamics defines that the temperature of a system proceeds towards absolute zero, but its entropy becomes constant or the change in entropy is zero. The third law of thermodynamics forecasts the behavior of entropy and the properties of a system in a unique environment, known as absolute temperature. This law assists in computing the absolute entropy of a substance at any given temperature. The resoluteness is traditionally based on heat capacity measurements. Example, consider a perfect crystal, a crystalline structure with no impurities or defects at absolute zero. According to the third law, the entropy of this crystal would be zero. This is because at absolute zero, the atom or molecule in the crystal are in most order state with minimal or no movement. What is a Carnot cycle? A Carnot cycle is defined as an ideal reversible closed thermodynamic cycle. Four successive operations are involved: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. During these operations, the expansion and compression of substances can be done up to the desired point and back to the initial state. The Carnot cycle, where four processes take place. Following are the four processes. In first, the process is reversible isothermal gas expansion. In this process, the amount of heat absorbed by the ideal gas is Q from the heat source at temperature of T. The gas expands and does work on the surroundings. The in B, process is reversible adiabatic gas expansion. Here, system is thermally insulated and the gas continues to expand and work is done on the surrounding. Now the temperature is lower, T. In C, the process is a reversible isothermal gas compression process. Here the heat loss Q occur when the surrounding do the work at temperature T. In D, the process is reversible adiabatic gas compression. Again, the system is thermally insulated. The temperature again rises back to TH as the surrounding continues to do their work on the gas. What is the entropy? Entropy is the measure of how many ways an arrangement can be made. Hence, the greater possibility of arrangement, the greater entropy, and the greater disorder. For example, if we have a certain number of balls on a table arranged properly, the number of possible arrangements will be less, resulting in lower entropy. Imagine, for example, a room where there is a sprayed perfume. The perfume molecules at one time are all constrained in one area of the room, but over time they reach every corner of the room and entropy increases or makes the whole system disorderly. Relation of second law of thermodynamics. Entropy is associated with second law of thermodynamics. It states that for any cyclic process, the entropy of a system either remains constant or goes up. If a process is said to be reversible, there will be no change in entropy. But in irreversible processes, the entropy always increases. It thus contributes to the natural tendency of system to disorder over time. Now we have to calculate the entropy of fusion of ice. Latent heat of fusion of ice is given 334.72 joules. Temperature at which fusion occurs is 273 Kelvin. Now we have to find the entropy of fusion. So entropy change during a phase change at constant temperature is given by delta S is equal to Q reversible by T. Q reversible is the heat absorbed during the reversible process fusion and T is the absolute temperature in Kelvin for fusion of ice. So substituting the values, L is given, T is given, we simply divide it and we have our answer. If the value is asked for molar mass in moles, number of moles, then we multiply it with molar mass of water. Now we have to solve some equations like this. First, delta S is equal to Cp logarithm of T2 upon T1. So from thermodynamics, we have this equation for constant pressure process dq is equal to Cp dt. When we put the value of dq from here to the first equation, we get this. Now this, as we know that Gibbs free energy is G is equal to H minus T. So when we take its derivative, this equation comes, and we know that dH upon dt at constant pressure is Cp, and the full derivative simplifies to dG is equal to dt at constant pressure. Now the next equation, this is for reversible isothermal expansion of an ideal gas, Helmholtz free energy. Delta A is equal to work reversible. We can write it as minus nRT logarithm of V2 upon V1, or nRT logarithm of P1 upon P2. Since PV is equal to nRT, V is inversely proportional to P. Work done upon charge is equal to T2 upon T2 minus T1. This is from Carnot engine efficiency. Eta is equal to W by Q2, which is equal to 1 minus T1 upon T2. And after taking LCM, this equation becomes in this manner, but this appears to be the reciprocal. So when we reciprocate it, we can get. Now delta GT is equal to nRT ln V upon V. This is for isothermal reversible expansion compression of an ideal gas. We know for an ideal gas delta G is equal to nRT log P2 upon P1, but for ideal gas law P is inversely proportional to volume. Thus we get P2 upon P1 is equal to P1 upon P2 at constant temperature and number of moles. When we substitute these values, we get our equation. This is a thermodynamic identity derived from the definition of Gibbs free energy. G is equal to H minus Ts. When we take its derivative, we get this. dG upon dt at constant pressure is minus S as derived in the above equation. Negative of work useful is equal to delta G. Gibbs free energy represents the maximum known expansion work, useful work that a system can perform at constant temperature and pressure. Gibbs free energy. Delta G is equal to maximum known expansion work, which is equal to negative of work done useful. Example of useful work: electrical work from a battery, work done in a fuel cell. Now delta AT is equal to nRT logarithm P1 upon P2. This is from Helmholtz free energy. A is equal to U minus Ts. In isothermal reversible expansion of an ideal gas, the change in Helmholtz energy equals the maximum total work. Delta A is equal to work, which is equal to minus nRT log V2 upon V1, and as we know that volume is inversely proportional to pressure, this equation becomes like this. Derivation of Gibbs-Helmholtz equation. Gibbs-Helmholtz equation gives the dependency of free energy variation with respect to temperature. Let G be free energy at temperature T. Find the variation of free energy at temperature T with temperature. Differentiate this equation. We have find variation of free energy with the temperature, that is delta G upon delta T. G is equal to H minus Gs. After differentiation we get dG is equal to dH minus TdS minus SgD. H is equal to U plus PV. After differentiating we get dH is equal to du plus PdV plus VdP. U is equal to Q plus W. Differentiate it, we get du is equals to dQ minus dW, and as S is equal to Qt and Q is equal to 2S Ts. We substitute these values and we get dQ is equal to TdS plus SgD. Work done is PV, so dW becomes PdV plus VdP. After substituting dQ and dW in equation 4, we get du equals TdS plus SgD minus PdV minus VdP. At constant temperature and pressure conditions, du equals TdS minus PdV. Substitute du from equation 5 in equation 3, we get dH equals TdS minus PdV plus PdV plus VdP. Minus plus PdV get cancelled and dH equals TdS plus VdP. Now substitute dH from equation 6 in equation 2. dG is equal to TdS plus VdP minus TdS minus STD. Plus minus TdS get cancelled and dG equals VdP minus STD. At constant pressure conditions, dG equals minus STD or minus S equals GT. Substitute value of GT in equation first and we get minus ST minus G upon T square. We take the LCM and now we get minus GS minus G upon T square. When we take the negative sign as common and we then it becomes negative at the outer side, Ts plus G upon T square. Now we know G plus Gs is equal to H. So this becomes minus HT square. This is our Gibbs-Helmholtz equation. Thank you.